Now, one way that we can solve systems of linear equation is using the matrix operation. Previously, we were able to solve the system of linear equation by using elementary row operation and converting the system of equation into an augmented matrix until um, the system is transformed or simplified into a reduced row echelon form. Now, what about applying the matrix operation? One practical application of matrix multiplication is representing a system of linear equation. Note how the system, so we will have here a 3 linear equations in 3 unknowns, which can be written as the matrix equation AX equals B, where A is the coefficient matrix and X will be the solution vector, column vector, and then BR is also a column matrix which consists of all the constant terms. Notice that when we perform the matrix multiplication, A times X equals B, we will end up with the system of equations. Say A11 times X sub 1 plus A12 times X sub 2 plus A13 times X sub 3 is equivalent to B1 is your equation 1. And similarly with the row 2 of this coefficient matrix when multiplied to the column vector, we have A21x1, A22x2, and A23x3. So when we add it together, is equivalent to B2, which is your equation 2, as well as with the last row multiplied to the column vector equals B will be the third equation. Now let us solve the matrix equation A times X equal to 0, where A is a 2 by 3 matrix and X is a column vector, and wherein B is simply 0. As a system of linear equation, AX is equal to 0 is also expressed as I mentioned, we have 1 times x1 plus negative 2 times x2 plus 1 times x sub 3. So this will be equivalent to 0. And you have 2x sub 1 plus 3x sub 2 plus minus 2x sub 3 is also equivalent to 0. Now, when we have the augmented matrix, recall that, okay, we will have the 3 columns here indicating the coefficients for the unknowns x sub 1, x sub 2, and x sub 3, whereas the last column is represents the constants in the system of equation. Now we can now perform our Gauss-Jordan elimination on the augmented matrix so that the reduced row echelon form is this. So we will have the leading one and below it is 0, and the next leading one and above that one is 0. Notice that there are more unknowns than the number of equation, and hence this system of equation has infinitely many solutions, and consequently we can find the parametric solution for the system. Notice that in row 2, we will have the expression x sub 2 minus 4 over 7 x sub 3 is equal to 0. So that x sub 2 is equivalent to 4 over 7 x sub 3. Now, since we can allow x sub 3 to be the free variable, so say let x sub 3 be equal to a parameter, let's say in this case to eliminate the denominator, let us say x sub 3 is equivalent to 70. Okay, and then we can now solve for, so that x sub 2 becomes 4t. Okay, so that, okay, so we will have a 4 over 7 x sub 3, but x sub 3 is 70. So therefore, x sub 2 is equivalent to 40. Now in row 1, we can see that x sub 1 minus 1 over 7 x sub 3 is equivalent to 0. X sub 1 is therefore 1 over 7 x sub 3, but x sub 3 is 70, and hence x sub 1 is simply t. We can now write the solution set. So we have x sub 1 is t, x sub 2 is equivalent to 40, and x sub 3 is equivalent to 70, or in coordinate form, we will have t, 40, and 70. Okay, so now since the solution is expressed parametrically, and we know that t is a scalar and it can be any real number. So since we will have x sub 1, x sub 2, x sub 3, which is our x, is equivalent to t. Okay, that would be t times 147. Then that means we can assign any value for t. Say if t is 0, then the solution is simply trivial. Whereas if t is equivalent to 1, then the particular solution is 147, and so on and so forth. So this system of equation has infinitely many solutions. Okay? Now, what are partition matrices? The system AX equals B can be represented in a more convenient way by partitioning the matrices A and X in the manner shown below. So first, we will have A, which is the coefficient matrix, and we will have X, which is our solution vector, and we will have B to be our constant. It's a matrix that consists all the constant terms in the system of equation. So if A and X and B, okay, as given as coefficient matrix, and then we have the solution vector, and then we will have the vector that consists of all the constant respectively of the m by n linear system AX is equal to B. Then we will have the coefficient matrix multiplied to x sub 1, x sub 2 up to x sub n is equivalent to B. Now, notice that with AX equals B, we can actually apply what you call the linear combination of column vectors. Now, how do we apply this? The matrix product AX can be expressed or is a linear combination of the column vectors A sub 1, A sub 2, up to A sub n that form the coefficient matrix A. We know that the first column is simply the coefficients of x sub 1. And the second column is simply the coefficient of x sub 2 plus the last column is the coefficient of the last variable x sub n. Furthermore, the system AX equals B is consistent if and only if B can be expressed as such a linear combination where the coefficients of the linear combination are a solution of the system. For example, let us solve a system of linear equation. So we will have the linear system that consists of 3 equations in 3 unknowns. We can actually express it as a linear combination. Say we identify our column 1 to be 1, 4, and 7, column 2 to be 2, 5, 8, and then column 3 to be 3, 6, 9, and then multiplied by their coefficients x sub 1 plus x sub 2 plus x sub 3 equivalent to 0, 3, and 6. This one is the linear combination. This one is actually the linear combination of the column vectors, which is equivalent to B. Now, using Gaussian elimination, we can show that this system has infinitely many solutions, and one of which is just x sub 1 equals 1, x sub 2 equals 1, and x sub 3 equals -1. So if we substitute x sub 1, x sub 2, and x sub 3 in the linear combination, we will be able to see that it is really a solution since it satisfies the equation. That's why it says here, B can be expressed as a linear combination of the columns of A. This representation of one column vector in terms of the others is a very important fundamental theme of linear algebra. Okay, so what we did today is we were able to identify the size of a matrix, perform operations on matrices such as addition, scalar multiplication, and matrix multiplication, and we were able to apply the concept of matrix equality. That means we can equate matrices if they have the same size, and also we can, from a system of linear equation, we can express it as matrix equation AX equals B. And also with AX equals B, we can actually express the product A times X as a linear combination of the column vectors. So that's it. In the next slide, in the next lesson, we are going to now solve a system of equation using a technique called matrix inversion. So see you next. Bye.